In question 8 you're given this diagram here, which is a robotic arm with an elbow type of thing here at Q. You're given the coordinates of R, and you're asked to find this angle here beta and this angle alpha. If you'll notice in this diagram, you're pretty much just given this triangle here and the coordinates of R relative to P. So my hint is you can use all kinds of trigonometry and coordinate geometry rules to get the answer. I've decided to redraw my triangle then with coordinates and lengths and everything attached to it. What I'm additionally doing is saying that this whole angle here is alpha, this PQ length relative to the horizontal axis, but I'm splitting that angle up into two different parts. A is the internal angle of this triangle, and B is then the angle between the horizontal axis and this length R of the triangle. Firstly, I want to get a bit more information about this triangle, so I'm going to find this length here, R, using the distance formula. So it's going to be square root of 24 squared plus 7 squared, and that gets you 25. Next, because in my triangle I only have lengths, I don't actually know any of the angles yet, I'm going to use the cosine rule as opposed to the sine rule to find out one of those angles. So the 25 squared being opposite this angle beta is equal to 20 squared, this one, plus 12 squared, this angle, or sorry, this length, minus 2 times 20 times 12 times cos of that angle beta. So you follow that through and you get cos of beta is minus 27 over 160. Now because I have cos of beta is minus, I have to think about my unit circle and where cos is negative. Since on the unit circle cos is effectively the x-axis, I know cos is positive over here in these two quadrants, and it's negative over here in these two quadrants. So I'm going to get two angles that are in between pi over 2 and 3 pi over 2, or indeed between 90 and 270 degrees. So I get my two possible angles then are beta is 100 degrees or 260 degrees. Now I'm told at the start of the question that beta can only be between 0 degrees and 180 degrees, so I know I can cancel this one. It's an invalid answer. Now if I go back to my triangle at the start, I now have three sides and I have an angle here. So I could use cosine rule to work out A, but I'm going to use a sine rule because it's just a very little bit shorter. Just remember, this isn't going to get alpha, this is going to get this angle A. With the sine rule then I have sine A over 12 is equal to sine of 100 degrees divided by 25. These are angles and they're opposite sides, that's the sine rule. So I got sine of A is equal to 0.4727. Now I know sine is positive now, so I'm looking at my unit circle again. Sine is positive in these two quadrants, sine being pretty much the y coordinate in this unit circle. Sine is negative down here. So I'm going to look for two answers in between 0 and pi, or between 0 and 180 degrees. The two angles I get then are A is 28 degrees or 152 degrees. We're told at the start of the question that alpha is in between 0 and 180, so the same must apply for A, but we can't use that at the moment. It doesn't really tell us which one of these is the right answer. What we do know is that beta and A are internal angles of a triangle, so between them they have to add up to less than 180 degrees, and if I have a third angle, then I know they add up to exactly 180 degrees. So if I know that beta plus A is less than 180 degrees and beta is 100 degrees, that I worked out just a moment ago, then if I add 100 and 152, I'm going to get 252, so that answer then must be invalid as well. I'm going to do the next bit just off to the side here, just because I'm running out of space a little bit. This is the underside of that triangle that I had before. So this length here, this P to R, is the bottom side of that other triangle. This is the x-axis here and just the height off the x-axis up to R. So I can just use basic trigonometric rules for this one because I know this angle here is 90 degrees. I know that tan of this angle is equal to the opposite divided by the adjacent, so it's 7 divided by 24, and if I get out my unit circle ideas again, the situations where tan is positive are in this quadrant here because both cos and sine are positive. Remember, tan is sine divided by cos. And this situation here where cos is negative and sine is also negative, so a negative divided by a negative will get me positive as well. So that gets me b is 16 or 196. Now of course b is an internal angle of a triangle, so 196 does not count. Lastly, I know that alpha is the sum of a and b, so it's 28 plus 16, and that gets me 44 degrees. So I now have beta and I have alpha, so that's the question finished. In part B, you're told that you're keeping the same setting that you had in part A, so this is the situation where r is 25 centimeters to the right and 7 centimeters higher than point P. The angles alpha and beta are the same, and it's asking you would an error in alpha or an error in beta of the same amount give a greater error in the location of r. So you can think of it like what happens when just one of those angles moves. So if I lock down point P then, and B is constant, or beta is constant, then I move the r through alpha, so that's what happens there. Alternatively, if I keep alpha constant and I lock down this point beta and I rotate this, then r is going to move as well. And the question is, in which scenario is r going to move the most if you rotate r through the same angles? If you rotate r through the same angle, locking down each of those two different points. Well, I can use the arc length formula that's on page 9 of the Formula and Tables book. The movement of r is given by r, this small r, which is the length p to r, multiplied by the angle through which it rotates. And I'm saying that the angle it rotates is this delta alpha thing, as in a change in alpha. And that's 25 times 1 times 2 pi over 360. Remember, the arc formula only works in when you have your angle in radians, so I'm turning 1 degree into radians here, and I get 0.436 centimeters. I do the same thing for the beta angle then. The distance q to r is 12, and the delta beta is just 1 degree again, so I take 12 and I multiply by 1 by 2 pi over 360, again turning this 1 degree into radians, and I get 0.209 centimeters. Since this 0.436 centimeters is greater than 0.209 centimeters, that means that a 1 degree error in alpha will cause a greater error in the point r, in the location of r, than a 1 degree error in beta. In part C then, you're told that the answer in B depends on the particular position of r. In other words, that the error in alpha doesn't always cause a greater error in the location of r than the same error in beta. You have to describe in what situations the error in alpha will cause a greater location error in r than beta, and vice versa. Just remember then that we said that the location error in r in terms of alpha is given by the length of this distance pr times the error in alpha, and the location error in r is, in terms of beta, is given by 12 times the angle error in beta. Firstly, I'm going to clarify what I mean by the small letter r is in the distance pr. It's given by this here, the square root of a squared plus b squared, where the coordinates of r are a and b, and p is at the origin. Since we're comparing the same error in alpha and beta, in other words that the error in alpha is equal to the error in beta, then the error in r given by alpha will be less than the error in r given by beta whenever r is less than 12, and the reverse is true, that when the error in the location of r given by alpha will be greater than that but given by beta whenever r is greater than 12. In part D, you're given a coordinate diagram with the same robotic arm with alpha, beta and r, and your job is to illustrate all the possible locations of this point r on the diagram. To work this out, I recommend you think about the extreme cases of alpha and beta, as in when alpha is at 0 degrees and 180 degrees, and when beta is at 0 degrees and 180 degrees. So first of all, let's think about the case where alpha is 0. Then q is right here at 20 on the x-axis. So if we vary beta, then let's say beta is 0, then the location of r is 12 centimeters away from here, which would lead us right to there. Next then, where beta is 180 degrees, you end up over here, where at the point 12 away from 20 in the other direction. And in between those cases, then beta will be all the cases that are 12 centimeters away from 20 in between 0 degrees and 180 degrees. Next then, let's think about the scenario where alpha is 180 degrees. So that means the point Q is right here at minus 20. Then if we say that beta is 0 degrees, the point R is going to be right here, 12 away from 20. And if we take beta as being 180 degrees, we end up over here at minus 32. That's where R is going to be when beta is 180 degrees. And at any other angle beta, the position of R is going to be given by this arc here, all these points that are 12 centimeters away from minus 20. If we next consider the cases where beta is always 0 degrees and we vary alpha, then this is the case here where they're both 0 degrees. So if we keep beta at 0 degrees and we increase alpha, we get this arc here that goes all the way around. All these points are exactly 8 away from the origin until we get to here where alpha is 180 degrees and beta is still 0 degrees. Lastly, imagine that beta is being kept constant at 180 degrees. So if we say that alpha is 0 degrees and beta is 180 degrees, that brings us to here. Now if we keep beta at 180 degrees and rotate alpha, we're going to get this arc here, which is 32 centimeters away from the origin. And we keep rotating alpha. Eventually we get around to back here where alpha is 180 degrees and beta is also 180 degrees. So at the moment all we have is just these lines here. Well, in fact, if we vary alpha and beta to just any particular random values that it could possibly have, then we'll actually get this whole area filled in here. So the possible locations of R then is just everything enclosed by this weird slug shape.